We are delighted to have Matias Cattaneo come and do this workshop today at CCPR. Matias is a professor of operations research and financial engineering at Princeton University. And at Princeton, he's also an associated faculty in the Department of Economics and the School of Public and International Affairs and the program in Latin American Studies, reflecting his interdisciplinary reach of his work. His research spans econometrics, applied math, data science, and decision science, with applications to causal inference and program evaluation, which are areas central to understanding policy impacts. He is widely recognized for methodological contributions to regression discontinuity designs and related non-experimental causal methods, and he has published influential work on robust estimation, inference, and data-driven decision techniques in both economics and statistics. He is a fellow PhD from Berkeley, and we are delighted to have you, Matias.
Okay. Thank you so much. I'm going to pick up on the last line. I'm going to say there are two types of graduates from Berkeley. Those who went back and those who are still trying. So there is nothing like Berkeley, I would argue. So yeah, it's quite amazing. Okay, so let me see if I can you see the slides a little bit? Yeah, hopefully you can do that. There are some extra stuff that we could get rid of, but I think it's fine. And then here there is code, which I hope you can see, or at least I'll make bigger as we go along. So I'll try to do some coding as well for you. Okay, awesome. So I was told that I'm supposed to give a 3-hour kind of mini workshop on something. And so that's something I chose to be boundary discontinuity designs, which is an area that I have been working on and off, and lately more intensely, I would say for about a year, and it's closely related to the work that Juliana has done, and therefore I thought it would be a good topic to talk about. But as you might see, as you might know, and I will show you in a couple of slides, is closely related to regression discontinuity designs. And since we have 3 hours, what I'll probably do is I'll introduce the basics of this particular problem and try to motivate why it's something worth thinking about, and in which cases you could, in principle, use it. But then I'll revert back to some ideas from regression discontinuity designs, and I'll show you some methodology on how to do identification, estimation, and inference in those contexts. And then I'll come back to this and connect it to this problem. So I have never attempted to do this before. So I've done slides and code. I have not done 2 sets of slides and 2 sets of code. So this is going to be a first for me. We'll see how it goes. If it gets too confusing, we drop it. And I'll do a break, right? In the middle? Yeah, bathroom break. Yeah, so I need to go to the bathroom every hour, more or less. So, you know, it comes with age, you know, yeah. The older you get, the more often you go to the bathroom, I think. Okay, good. So, and the topic of boundary discontinuity designs is based on a sequence of papers that we have completed and we're currently working on. It's a rather niche topic in itself, but nonetheless, I think an important one. There are certain settings where this type of design for treatment effects and causal inference is relevant. The most common one is either the context of geographic regression discontinuity, or the context where you have more than one score, and therefore the boundary the region determining treatment assignment is one that is not really determined by a single cutoff point, but rather by a bunch of those. And so that would be kind of the idea. So this work is all joined with Rocio Titiunik at Princeton, and Ray, you also at Princeton, a grad student of ours. And in terms of the talk, I'm going to mostly focus on this paper here that is coming out as part of an invited lecture for the World Congress of the Econometric Society. And it's relatively easy to read. So if you're interested in something that doesn't have a lot of math, and it has mostly ideas, and in fact, we try to give it a spin, a little bit of history of thought, if you like. So we started from the very beginning, where these ideas of boundary discontinuity designs had first been used and then how they evolved into what nowadays people tend to do. And as a result of that, we also came up with some methodology, which I'm going to focus most of the talk today. Okay, great. So what I'll do is I'll give you a short introduction to boundary discontinuity science, what the challenges are, how it's often used. And then after that, instead of jumping straight to the different methods that people use in practice, there are often three types of approaches that we identified in most empirical papers. What I'll do first is I'll revert back to classical regression discontinuity, build some ideas in case that you haven't seen them before. And then once you see how that's done, it can be quite easily deployed with modifications to these cases. Okay, so what is the basic idea of boundary discontinuity science? Well, as I said already, it's essentially a generalization of traditional regression discontinuity science. The two most common cases are either settings where you have more than one score that determines jointly treatment assignment, or in the most classical case possible, you have a geographic RD design. So units are located on space. There is some boundary, often a geographic boundary if you like. And then units that are on one side of the boundary are assigned to treatment group. Units that are on the other side of the boundary are assigned to control group. And just like in traditional regression discontinuity science, here as well, the premise is at the end of the day that units locate on space in a non-random way, and often they select based on observables and unobservable characteristics that affect outcomes of interest, and therefore makes quite difficult to identify causal effects of policies or treatments. But nonetheless, if you were to zoom in to units that are right on the boundary, in this case, the boundary is a one-dimensional curve, if you like, because it's a geographic boundary between two states or something. Then as you zoom into the boundary, you hope that all these differences that units had tend to disappear, right? So there is this notion that as you get closer and closer to the edge of eligibility or the edge of treatment assignment, all of a sudden these observable and unobservable characteristics that differentiate units on one side or other the boundary, they tend to become less and less pronounced, right? And so this is at the core of the idea of RD designs or boundary discontinuity designs. And of course, in geography, it's often the case that that assumption is fundamentally violated, right? So people select in space all the time. We choose where to live based on the schools that we like. And it will be rarely the case that you would randomly happen to choose a house without thinking of all the kind of observable and unobservable characteristics that ultimately might be correlated with the policy of interest. And so we'll talk about that a little bit along the way. But if you take this design as given, or if you work in the special case, or maybe perhaps the more general case of multi-score RD, there are settings where these type of concerns are not as pronounced because units are not able to manipulate their geolocation that easily. A prototypical example is the work that Juliana has done, and I'll show you a little bit of that as a motivating example. In those settings, manipulation is much less likely, and so we can leverage ideas from regression discontinuity designs to the context of boundary discontinuity design. And so if you look at the literature, both empirical and methodological, had tried to grab everything that was known at the time, and this, of course, is a moving goalpost over time, but whatever was known at any point in time, researchers tend to go to the literature, learn whatever it was available for one-dimensional classical regression discontinuity designs, and then they try to port it, to deploy it, and use it in the context of boundary discontinuity designs. And so that had led to a variety of approaches, empirically speaking, with very little guidance in terms of methodology. And so what we try to do in this sequence of papers is to first identify what are the best or the worst, or what are the different methodologies that people use, and then try to either improve on them or warn you about potential issues that they may have that are specific to the fact that you brought something that was working well in one dimension, and all of a sudden, when you bring it to a two-dimensional setting, things stop from working equally well, right? And so to be more precise, in the literature, there are basically three approaches to analyzing boundary discontinuity designs, and I'm going to walk you through all three of them with you. The first one is what we refer to as the pool approach, and this tries to mimic the one-dimensional RD design in a very special way. And then there are two other approaches that we're going to refer to them broadly as distance-based or location-based. And all these three approaches are different ways of doing the same thing, which is estimating treatment effects, policy effects, using boundary discontinuity designs. Okay, good. So if you're interested in software and empirical applications, we have a bunch of those in this website that contains quite a bit of empirical stuff for you to play with. So here's a basic example, trying to bring a little bit more ideas to this. So on the left, you have the case of two-score RD. So this is a boundary discontinuity design. In this particular example, this is motivated by an application that is coming later. You will have some sort of exam in one dimension, and you will have a poverty index in another dimension. And here eligibility is built on the idea that you have to clear two cutoffs as opposed to one, right? So the two cutoff meaning that you have to score sufficiently high in some exam, and then you have to also be sufficiently poor or sufficiently rich or whatever in the other dimension, right? And so, as you can imagine, this could be viewed as a one-dimensional RD. So you can always think of, well, let's dispense of the other direction and focus only on one score at the time. And this is something that people have done, and it's one of the methodologies I'm going to discuss today. But as you can imagine also, there is something interesting to be learned if you were to think about this from a two-dimensional perspective, right? So in a sense, the key is that you move away from having a single scalar cutoff that determines eligibility on each of the two dimensions to have effectively a boundary. And this boundary is this one-dimensional curve, which on the left happens to be very simple, very simple function, if you like. And so it happens to be linear, and then at some point it has a kink, and then it's linear again, right? And this is a reflection of the treatment assignment mechanism, right? So here we are assigning to treatment units in a very special way. We are using a Leontief type assignment mechanism where you have to clear both of the cutoff in order to be eligible. And so this area here is typically called the eligibility area, and all units that happen to land anywhere in this region are assigned to treatment. All the units that are located on this light gray region are assigned to control, okay? And so right here, you can start thinking about, okay, what is an interesting treatment effect, right? So you could say, well, you can, for example, position yourself here in the boundary and ask the question, what is the treatment effect there? Or you can move yourself farther down, maybe farther down to the kink, right? You can keep going. And so effectively, what you are discovering is a family of treatment effects. Those treatment effects are described by the location along the boundary, right? And so there is a notion of heterogeneity here that can be exploited, where, for example, perhaps treatment effects in this area of the boundary of eligibility corresponds to treatment effects of units that are quite rich, relatively speaking. Suppose that the poverty index means rich to the left, poor to the right, right? So units here are very, very poor. Units here are very, very rich. You are eligible if you are sufficiently poor, right? So you need to meet a minimum level of poverty. So for all units that have this level of poverty, you can still ask the question, of course, what is the level that you acquire in your exit exam? And so that determines the notion of heterogeneity, where students here are among the richest that they could have been, and also the most successful they could have been as measured by their exit exam, right? And as I move down this line, what I'm looking at is students or units for which their success in terms of exit exam is going down, but their poverty is not changing, right? And so there is some notion of heterogeneity that goes down this way, say, and then once you reach the kink, the notion of heterogeneity goes that way. And of course, this is very much intuitively depending on the geometry of the boundary. This boundary is very simple. It's a boundary that is linear, and then it has a kink, and then it's linear again, right? And so that's going to be an easy case, unfortunately, or fortunately, depending on your problem. So this is going to be a good case, an easy case. Now, on the right, you have a similar type of boundary discontinuity design, but this one is based on geography. And this is motivated by a very, very famous paper. At the time, it was not analyzed exactly like a boundary discontinuity design. But I mean, if you read the paper, we went back and read it in honor of the authors. It's Karen Kruger paper. You might have heard of it. It's a very famous paper that tried to analyze the effect of minimum wage, right? And so the core idea that they had in mind is they tried to compare two states that have different minimum wage, and then they try to understand how that affects employment, wages, and so on and so forth. And the way that they do it is, well, they used to be at Princeton, poor them, and so because they were at Princeton, they were comparing New Jersey and Pennsylvania, right? And so the gray area is New Jersey, where Princeton is, the right area, the left area, the red area is Pennsylvania, and they have a differential they have different minimum wage requirements. And so again, the idea that they had, and in fact, they implemented this way, even though they didn't use the language of boundary discontinuity designs, was to basically try to grab restaurants or other type of businesses that were close enough to the boundary. And then what they try to do is to compare how workers on restaurants on one side of the boundary vis-a-vis restaurants on the other side of the boundary, how different things were for them. Right? And these kind of things are, okay, good. And so they had the notion of localizing, right? So they had this notion that maybe restaurants in this area were not that comparable with restaurants in that area, but restaurants that were close enough to the boundary, they were comparable. But then again, what they did, however, is that they didn't kind of walk themselves around the boundary, like I described a minute ago on the left, but rather what they did is they kind of constructed a band around the boundary. They catch all the units that band caught, and then they just look at the difference on both sides, right? And so in a sense, they changed the parameter of interest, right? Because what they were doing there is some sort of aggregation. So they were kind of saying, no, I'm not going to look at the heterogeneity along the boundary, which maybe in the case of geography is less or more interesting because it reflects geography. But ultimately, what I'm going to do is I'm just going to form a band, cover this band, and then I'm going to just do a difference in means or a regression analysis, and I'm going to compare all people on one side against all people on the other side. And so intuitively, you can imagine that this is a little bit of aggregation of heterogeneous treatment effects, right? So you're kind of aggregating them in some way by pooling all that information together. And you could do the same here, by the way. You can construct a band, and then analyze all these students along the band. You can construct a different band here, do it the same way. You can even do a single band like this and do it this way, right? And you can also do that. And so that ultimately are all ideas that, again, in one dimension doesn't really matter, but in 2 dimensions or more, it starts to matter. So how you actually do these things matter. And very importantly, as I'm going to show you in a minute, the geometry of the boundary matters. If the boundary is nice, and nice has to be defined, but if it is like linear, it's a good boundary, it's easy, then things are going to work well. If the boundary is more like on the right, well, there is an interesting philosophical discussion, which I'm not going to get into, but there are some philosophers that believe that all boundaries in geography and many other natural sciences happen to be fractals. Okay, so fractals are particular curves that have very, very high variation, and they're essentially very discontinuous in a sense. And so that will generate some problems, because when you try to estimate things along this fractal, well, if the thing is jumping a lot and doing very crazy stuff, then your aggregation might get affected by it, right? So that's kind of the idea that operates in the background. So I'm going to show you some pictures to think about that. Okay. So let me try to introduce some notation, because I think it's important. So we're going to define a script B to be this assignment boundary, right? So this is, I'm sorry to throw a little bit of a jargon here, but you have to be aware that we're working on the plane, and we're looking at a one-dimensional function that lives on the plane. So that thing has a name. It's called a manifold. It's a one-dimensional manifold. It's simply a one-dimensional curve that lives on a two-dimensional space. And so that typically is going to be our assignment boundary. And the geometry of that boundary is going to matter a lot. So unfortunately, this will have implications on how you actually do estimation and inference and what it means to get results for something like this. Okay? And then I'm going to use this notation A0 and A1, which stand for assignment regions. And so A0 is going to be the control group, and A1 is going to be the treatment group. So this area here, for example, will be my A0, and this area here will be A1, and the same between the two states. Okay? So far so good, nothing crazy. Now, the other important thing, of course, is that we have a bivariate score, and this is just the geography in location. It's a geolocation, right? So this will be latitude and longitude in the geographic case, or maybe the block where you are in a census tract block, or maybe it's just the score that you receive in your exam, and also the poverty index that you're assigned to you. And so this will be the bivariate type of variable. And then I hope most people in this audience is familiar with this is the idea of potential outcomes, right? So we're going to assume that units have two potential outcomes, y0 and y1. And then depending on which assignment they receive, they will reveal a potential outcome 0 if they are assigned to the control group, or a potential outcome 1 if they are assigned to the treatment group. And here, I mean, I'm going to just brace through this, but I hope you are familiar, and more importantly, you are critical. In one-dimensional settings, this type of framework makes sense, and I will be very happy to entertain it, at least to first order. But in this type of settings, often it doesn't make that much sense. And the reason here is spillovers, right? So this type of assumption is completely ruling out spillover effects. But in geography and sometimes in other settings with two scores, you might have quite a bit of spillovers, right? And so these spillovers are not assumed, rather we are assuming a way. And so we're going to treat all this data as IID, and that might or might not be a good assumption empirically, okay? And so that's something to keep in mind, especially in geographic RD setting. Okay, but for the purpose of today, I'm going to ignore that, and we're not going to think about spillovers. And then the final piece of notation on the basic model is the idea of treatment assignment. And here the treatment assignment means that if you land on region A1, you're assigned to treatment. If you land on region A0, you're assigned to control. Pretty straightforward, nothing crazy, okay? And now, the other thing that we need to define is notions of distance. And so instead of defining them with mathematics, I'm going to show you a couple of pictures, so you kind of see what it means to construct these notions of distance and how we're actually going to estimate things along the boundary, okay? And so here's a basic application that I'm going to use, which Juliana was very kind of sharing all this data some time ago with us. And so I'm going to leverage that data. See, this is a very well-known, I hope for you guys here, conditional anti-poverty program, where the idea basically is that, well, unconditional, I guess. The idea basically is that you are students graduating from high school, and you take an exit exam, which is known as Saber 11, and you need to score sufficiently high in your exit exam in order to be eligible for the program, but also you need to be sufficiently poor in order to be eligible for the program. So here is a poverty measure, here is an academic measure, and then ultimately all the students that are in this region would be eligible for the program, and all the students that are outside in the complement of that region are not eligible for the program, right? And so again, just to practice, students that are up here are students that are poor, right? Very, very poor, right? This is a poverty index, so this way you get poorer, right? But also you perform not as well in the exit exam, right? And so as you move down this boundary, you are becoming richer and richer to the point of not being eligible anymore, but you are not really improving in your quality academic skill, right? And then once you hit the kink, you start moving this way, right? And now the students are as rich as they can be to be eligible, and they start to get, quote unquote, smarter, right? Smarter here is a loaded word, but certainly they are doing better in the exit exam, right? And so comparing treatment effects here versus here is quite different, right? So this will be for units who are quite poor and not very good academically, in terms of the exit exam anyway. And these ones are students that are relatively richer to the margin of eligibility, and also they are doing quite well in the exit exam. So now I can map all this language into the language that we have discussed so far. So you have these high school students indexed by I, and you have these two variables that determine where you land on this space, which is how well you do in the exam and how poor you are. Okay, great. And so in this very simple case, the boundary is very simple, right? And this will help us a lot, but even here, something will happen. And this is kind of cool, as you will see in a minute. This boundary has something that is very smooth and nice, and then it hits the kink, right? Change direction, and then it becomes cool and nice again, right? And so I keep emphasizing the kink because the kink is gonna play an interesting role, as you will see in a minute. Okay, great, excellent. So the outcome here is whether you completed college, but that's not that important. Okay, so let me show you a little bit of how people have approached this problem from the very, very beginning, right? So they start with this simple scatter plot in R2. And one thing that people have thought of doing is basically to collapse everything and kind of make it a one-dimensional RD design, right? And so here's where the connection on with RD designs are going to come back into play. So what people do is people say, well, I'm going to construct some sort of band, and then given the band, this cover of the boundary, I'm going to catch all the units that are there, and then I'm going to just do a simple regression analysis, right? That's kind of the idea. So this, of course, is estimating a single parameter, a single treatment effect, which we call here tau hat, right? And it's nothing more than the difference in means, if you like, right? So you catch all the people on one side versus all the people on the other side. And so the way that they typically do this, of course, it's not the only way, but the way that typically people do this is by grabbing each observation and finding the closest point to the boundary, right? So this sometimes is called the perpendicular distance, or whatever it's called. It's basically you find, okay, for each unit, you find the point that is closer to the boundary, and then you assign that distance for that unit, right? Regardless of where they are located in a space, right? So a unit here that is distance units, 3 units of distance, and a unit here that is 3 units of distance will belong to the same band, right? Because they're both 3 units away, right? And so visually, the band kind of looks like that. Okay, can you see that? So that's pretty straightforward. It's not very difficult to see, but if you stare for a minute, you will see that already something cool happens, right? And this is not immediately obvious, but once you think about it, is, right? So when I come from the treatment group in this case, it's very easy to measure that distance, right? Because you can imagine, right? So all these units are up to this point equidistant to the boundary, and the equidistance is such that the boundary, the edge of the band looks like the boundary. Can you see that? It looks like the boundary. It's kind of cool, right? So it also is like a Leontief curve, right? And everything here belongs to that region, no problem. Okay, so that's pretty cool. But now let's do the other side, right? The other side is kind of a little bit interesting because I position myself here. I am 3 units of distance to the boundary. I move myself down. I continue to be 3 units from the boundary. And I move myself down, and I continue to be 3 units from the boundary. But then something happens, right? If I were to construct another Leontief, then I would be farther than 3 units away from the boundary, right? So this kink generates something weird, right? It metrizes distance in a particularly weird way, right? And so it actually happens, and you can show this, that this point here is in a sense irregular. The kink generates a notion of distance that is actually curved. It's not perpendicular, if you like, as it was before, okay? And so that immediately should bring you to think about, okay, would everything work anyway? Would everything work no matter what, right? And of course, this is just one kink. So one kink is not a big deal. But imagine now that you don't have one kink, you have 20 of these kinks, right? So then all of a sudden, these areas are going to start having all these bumps that depend on how you metrize the distance to the point, right? And so actually, that's going to matter quite a bit, right? So as you will show you in a minute, more from a technical perspective, but it will have some implications for practice. It will actually generate these points of irregularity that now you have to start thinking about. So how actually the estimation goes, under which conditions this works, and so on and so forth. Okay, and so I'll try to explain some of those ideas in a little bit. Okay, but practically speaking, it's super easy, right? So you construct this band, you catch all this data, and then you work with it, right? And so you might have seen multiple papers where people do that. Okay, and so here's an example of how the band would shrink, right? So here we go, large, small, right? So what is the idea here? Well, just like in RD designs, right? So if we think that identification happens at the boundary, we would like to localize as much as we can. And localization here is in the one-dimensional world, it was a simple shrinking of the bandwidth, if you like, and it was a region on each side of the cutoff. Here you have this issue where the band is shrinking entirely. So the band is shrinking, right? So this has a name. It's called a tubular in mathematics. But for our purposes, it's just a band. And the only thing that we are saying is that this band is shrinking. And now we need to understand how, as you shrink the band, how the estimation happens. Right? That's kind of the idea. So what are we getting out of this estimation in some sense? Okay, so how do people implement this? Well, it's actually quite simple, right? So they grab all the data on one side, all the data on the other side as determined by the band, and then they run a difference in means, right? And so how do we write a difference in means? Well, we run the regression of y on a constant and being on one side of the boundary indicator. And then, of course, we only do it for the units that happen to be di units away from the boundary as metrized by this perpendicular distance, right? So it's super easy, super straightforward to implement. And there is nothing crazy here, except that, of course, you're using this weird, or, I mean, not weird, but this notion of distance to the boundary, okay? Excellent. And so once you have that, you can recognize immediately that this is a one-dimensional RD design, right? So the only difference is that we grab the 2 dimensions, we map them into 1 dimension through this notion of distance, and now we're just doing RD in one dimension, right? And that's exactly what you're doing, and you're getting back a single point estimate of some parameter, and we need to understand what that parameter is, okay? And so without going into too much detail, you can imagine that this procedure can easily be mapped in the usual RD plot, right? So 0 means that you are on the boundary. So all the units that are 0 distance, no matter where they are located geographically, 0 distance to the boundary. And then as you open up control by H, you are catching at the same time all these units that are maybe 1 unit away from boundary, 2 units away from boundary, 3 units away from the boundary, and so on and so forth, right? And so that is controlled by this bandwidth here, right? And so here's an example. I chose 10 units of distance. And so I got all this data that happens to be 1 unit away, 2 units away, and so on. And I plot them here, right? So these are the 1 unit away, 2 units away, 3 units away, 4 units away, up to 10 units away, right? And you kind of collapse all that, or you pull all that, right? And so that's why this methodology is called pooling, right? Because you're kind of pooling all this data and treating it as a one-dimensional thinking, okay? And now I hope it doesn't take a lot of effort to think about, okay, what are you really estimating here, right? Well, you're gonna be estimating some weighted average along the boundary, right? Because as you shrink this band, you're gonna be kind of averaging along the boundary all the effects that would have come out at each of these points individually, and you're kind of averaging them along, right? That's kind of the idea. Okay, so this methodology is extremely popular. So if you follow the literature, I think it has been popularized by Melissa Dell with some application in Peru, and a bunch of other people have followed that. And nowadays, most people use this for simple one parameter treatment effect estimation. Okay? And so with a little bit of work, you can show that as you shrink the band, so here I show you the large band, the medium-sized band, and eventually the very tiny band, you're effectively shrinking, 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 and as you shrink, what you're really estimating is a very special weighted average treatment effect. And so what is the weighted average treatment effect? Well, I hope it's not super surprising. What it's doing is estimating, hypothetically, every possible treatment effect along the boundary, and then it's kind of averaging it by weight, using as weights the relative density of data along the boundary, right? So here, this f divided by the integral over the boundary here, well, that's kind of a conditional probability, right? So it's kind of saying, look, if I integrate along the boundary, well, regions where density is high, we're going to have more data, and my overall treatment effect is going to get pulled towards that, right? And so you're going to be disproportionately weighting maybe regions of high density relative to regions of low density, right? And that will report a single effect that kind of averages what you could have done, which is estimate all the effects one by one along the boundary, right? And so it has a good and bad things. The good thing is that you don't have to think about anything. You literally grab your data, you compute the distance to the boundary, and then you run classical one-dimensional RD designs with the caveat that you are estimating a single parameter, which is this weighted average, right? And so, as you can see now, if we have methodology for RD designs, as we do, then the question is, how do you map that methodology into this problem? But there is nothing fundamentally difficult or new, except for understanding how this approximation works, okay? And so today I'm not gonna discuss a lot of that, but you can imagine that as the band shrinks, you are kind of approximating a function along the boundary, and this function has to have certain nice regularity that depends a little bit on how irregular or regular the boundary itself is, right? So for boundaries that are very regular, this type of approximation may actually break down. Okay, but what is very important is that you are ultimately averaging effects along the boundary. And so some people have said, well, hold on a minute, if we're gonna average effects along the boundary, why don't we just first estimate those, learn about them, and then average them afterwards, right? And so that leads to the other two methodologies that instead of targeting this sort of average effect, what you would do is first estimate the effects along the boundary, and only after, if you wish, you can average them. Or maybe you're gonna do something else. Maybe if you're interested in policy, you could say, look, I don't really care about the average effect along the boundary. I might care about the largest effect. Where is the largest effect located? Is the largest effect in this region? Is the largest effect in that region? Well, that will be a different kind of question, right? You wouldn't average the effects, the heterogeneous effects along the boundary, but you will be looking for the largest effects. So you will be looking for the supremum or the max instead of the average, right? And that will be a different thing to think about. Okay, excellent. So just to wrap up the introduction, let me quickly show you how people would do that in this case. So again, we're back to this example, but now instead of doing this band and averaging everything at once and just mixing all together, we're gonna be a little bit more careful. So what we're gonna do is we're gonna form a grid of maybe 40 points. And now for each of these points, we're gonna again view that as a one-dimensional RD design, right? But now instead of averaging and building these bands and doing all at once, what we're gonna do is we're gonna position ourselves on any one point on the boundary, let's say B10, and then we're gonna do local approximations just like we would have done it in one-dimensional RD designs, right? Because now effectively, this is like a one-dimensional RD, right? You still have the issue that units are located on space, but ultimately you're facing this one cutoff, right? And so you know that all the units on this side are treated, all the units on this side are controlled. So at the end of the day, it's a matter of how we metrize, how we actually approximate for that one point. And then after we do the B10, we can go ourselves and do the B15, and then eventually the B21, which is a kink. And then we can keep going and do ourselves all the way to B40, right? So this will be like, you don't, I guess that's why one is called pooling and the other one is not. In the pooling, we kind of catch all the data and run a single RD. In this kind of setting, we first discretize the boundary and then we run 40 RDs, right? That's kind of the idea. And then we get 40 treatment effects, and then we need to do something with those 40 treatment effects. We can plot them, we can aggregate them, we can take the largest, we can do something to them, but you're gonna have like a curve, right? So effectively, what we're doing here is kind of estimating a curve along the boundary, right? That's kind of the idea. So which curve is that? It's exactly this curve. So you are estimating the treatment effects for each location along the boundary. And so once you have that curve at hand, then you can do whatever you want to do, right? You can aggregate it, we can do something. You can even try to reconstruct this one, right? You can even do that, right? So you can first estimate this guy and then try to reconstruct that one by taking the average, right? The weighted average, and see how different those things are. And again, theoretically, they at least, and hopefully empirically, they shouldn't change too much. They shouldn't be that different, right? It's a matter of how we do the analysis more than what parameter we are targeting. Okay, good, excellent. So in order to do this estimation from B1 to B40, on the grid, you need to choose how you localize, right? And here is where people, again, got very creative. Some of the things, most of the things is not us. I mean, we're just reading the literature and seeing how people have done it in different ways. So here, you need to decide what close is close, right? So you need to decide, okay, I'm in B10, is this unit close? Is this unit close? Is this unit close? Is this one close, right? So somehow we need to determine what is close and what is not close. And so there are two ways to do that. So one way is to first compute the distance that every unit has to B10, right? So for example, you can compute the Euclidean distance, right? Or I've seen papers where people compute the walking distance, right? So there is this cool paper in the AR where they look at how many blocks do you have to walk until you get to a water dispenser or something like that, right? And so again, that distance is a little bit different because it's a distance that will take into account the geography of where you are doing this, right? Or there was this paper where they're looking at a geographic RD and they're mountains. And so sometimes in order to get from the boundary to a point, you have to walk through a mountain, right? And so that obviously, it's arguably, it will be a longer distance than if you have a straight, flat region to walk, right? And so you can actually metrize that. So ultimately, you need to define a way of measuring distance. And so once you have distance, you will assign to each point here how close they are to B10, and then how close it is to B10, every single one, right? And so this one here will be close. This one here will be farther away, depending on the distance, of course, the geometry. And then this one may be or may not be, and so on and so forth. Okay? But once you have the distance, now again, you have a one-dimensional variable, so you have a one-dimensional RD. You're done. So you can apply again RD designs, right? So you do it not 1 time, but 40 times. And each of time, you do it with one-dimensional distance, right? So that's pretty simple. And so this is what we call sometimes the local regression based on univariate distance, right? Because that's exactly what you're doing. You're just computing, reducing the bivariate structure to a univariate distance-based structure, and then you just run the RD that you like, okay? And then, again, once you have that data, you just rely on things that we know, or at least seemingly you rely on things that you know, and then you are in business, okay? But an alternative to this would be to say, no, let's not use distance. Let the data speak for itself. And so in that case, what you would do is you will, again, position yourself on B10, say, and then what you would do is you would directly use the bivariate location information, right? And so this will no longer be the classical RD setting. This will be outside the classical RD setting because now you don't have one score, you have 2 scores. One is longitude, one is latitude, or one is poverty, the other one is exam. Great. And now you're going to feed both together for estimation. right? And so at that point, you move outside the classical RD setting because now you have a bivariate score. So you can transfer the ideas from RD, but you cannot transfer the software from RD, right? Because now you have a bivariate score and you have two cutoffs, right? And so you need to do something about that.
The location-based design is important that the boundary be linear. Because if I'm only having all these different points, why does it need to be maybe a shape? Why can't it be just a disbursement of points? So just like a water station.
That's super great question. So you are of course taking all my thunder away, but that's okay. I don't mind. I mean, great questions should take the thunder away. So let me answer your question right now. And what I'm gonna do is I'm gonna do a bunch of plots so you appreciate the subtleties of these. And I agree with you. It seems like in a location-based setting, it wouldn't be much of a problem, right? Because if you look at a boundary that maybe looks like this, and then like this, and then like that, then of course you position yourself here, and then you just look at all the bivariate location relative to that point, and then you position yourself here, and you still look at all the location relative to that point, and that's perfectly fine. However, there are other cases that arise naturally in when you go from dimension 1 to dimension 2 or higher, where things can get a little bit tricky. So here's an example. Suppose that this boundary looks like this, but now it also does this.
No,
Okay, so you have the boundary like this, but now suppose that the boundary does like this. Okay, so this is called a crust in mathematics, right? So basically what happens is that you have regions with very low density of data, right? And in those regions of very low density of data, you cannot really identify or estimate treatment effects, right? So when you have things like that, like for example, like this, right? So then in those regions, you're not gonna able to estimate anything here, for example, right? And so again, in the application that I'm discussing, that doesn't happen because it's a very nice linear one kink situation. But in geography, this happens all the time. Like when you actually look at geographic boundaries, often the geographic boundaries do all this kind of crazy fractal type stuff that you cannot really learn anything about, right? And so it matters, again, from an econometrics perspective, our job is to give conditions to understand situations like this. From a practical perspective, the question is, can you learn something, right? And so if you have very little data like that, then it's very, very hard for you to learn something, right? And that's kind of the idea. And so again, mostly this talk is not about giving you recipes, but it's more about thinking about the problem, right? Thinking through the problem. So as you try to apply these in certain geographic settings, you have to think about, okay, am I really learning something here, or is just artificial, right? So you're just extrapolating artificially, but you're not really getting anything out of your data. Okay, cool. Good question. Any other questions so far? Yeah.
So I have one question. You have here in the two-dimensional score, two scores that are completely different, right? One is poverty, the other is income. And so the way you decide the bandwidth that you're gonna use is also determines your treatment effect. And you could do it in a way that you get a biased estimate. So for example, you choose a super large boundary on one of the dimensions, a very, very small one on the other one. So I would say you have two options. Either you standardize or normalize the data before starting, one option.
Yes.
The other option is you use a percentile type of notion of distance. So you say within the 90th percentile and something like that as a notion of distance. But then at that point, your average treatment effect, so in the first case, maybe not. In the second case, your average treatment effect becomes maybe a simple average of the treatment effects.
So I regret inviting Octavia because she took all my thunders away again. So why did I do that? All I had to say, no, it's a closed UCLA only people talk. Yeah, no, you're absolutely correct. Of course. Another thing I was going to say in a little bit is that when you choose your distance matters a lot now because, as you correctly pointed out, the variables that you might be looking at might even be in completely different scales, right? And so the scaling of the data happens to matter a lot. If you do a location-based, or if you do the bivariate location-based analysis, the bandwidth you would have to make the bandwidth separate for each direction, right? So if you did a single bandwidth, I mean, again, in the limit, all these things wash out, but in practice, it will matter a lot, right? So, because imagine that maybe your poverty is in thousands of dollars or, well, Colombian pesos, yes? And your exit exam might be from 1 to 100, right? And the points that you got or the ranks that you rank in your, so it's completely different scale. So you cannot use the same bandwidth. What are you doing really? Well, in the bivariate world, but also in the distance world, effectively, you're constructing a notion of geometry, right? Because think about it. You start with Euclidean distance. Euclidean distance would be, okay, this is a boundary, right? And so Euclidean distance will be a ball, right? So it will be everything that is equidistant in an L2 notion, in a quadratic notion, right? Euclidean distance. But now, if you start deforming the distance because you need to reweight the directions, now maybe what you're doing is like ellipsoids, right? So effectively, you will, if you have, for example, in one direction, you have more variability than in the other. So maybe your Euclidean distance gets weighted by each dimension because you have to scale the data, as you said, right? In fact, our software does that. Our software doesn't use really Euclidean distance. Our software grabs each of the two scores, divides them by the standard deviation first. So it kind of deforms the geometry, right? Because now it gets weighted by how much variability each of the two scores have, but now they're on the same scale, right? Because they're on percentage points or standard deviation points, right? So the bandwidth becomes a notion of a standard deviation. And then what we do in the software is after we do all the analysis, we take because the bandwidth doesn't matter, then we actually change it back. And then we give you a notion of what in the real scores, we grab the bandwidth and multiply by the standard deviation in each direction. So effectively what we're doing intuitively, right, is you start with a circle, you apply the standard deviation in each direction. So effectively you are measuring distance in a kind of ellipsoid way. And then we learn what the bandwidth is in each direction. So this is like H1 or H2. But in reality, what is that? It's just a standard deviation times the bandwidth that you start with. And so that's kind of how we do it. We kind of stretch it in one direction or the other. Is that a great idea? I don't know, but that's kind of what you can do. But I completely agree. So ultimately, your point, again, I said, I'm not going to give you recipes. I'm going to make you think about it. How you choose the metric matters. And how the data scale matters, right? And so how you interpret even this band, right? So again, nobody mentioned this before, but it's the same point. Even when you look at this band here, this band depends on the distance, but this distance is in 2 dimensions. So again, the scale matters, right? The scale in each dimension absolutely matters, absolutely matters. For applications. For theory, it doesn't matter because I'm going to take all the limits shrinking to the point, and so all these things wash out, but practically it matters a lot. You mentioned a second procedure. What was the second procedure? Because the scaling one is the one that we do. What was the other one that you suggested?
Chantel's.
Oh, okay, sure. Yeah, exactly. It's like ranks.
Yeah.
Ranks. Yes, exactly.
Ranks,
Yeah, ranks. Exactly. So yeah, ranks will be, oh, I hope it didn't break because that would be bad. Okay, let me try. So ranks, it will be another option. So yeah, it works. Awesome. So rank will be another option, but we didn't do that. Yeah, we just do plain vanilla standardization. Then we, effectively we grab a Euclidean norm, then you deform it according to the scale of the standard deviation in each direction. Then you average across that, and then you change it back. And then we report that.
Do you know if there's like a significant difference between standardizing and normalizing?
We didn't try. So again, I mean, there was an old literature, you guys are all very young for this, but when I was in the PhD, what it was totally in fashion was matching estimators, right? So matching estimators do this idea of selection observables where you find units that are very close in terms of observable characteristics. But again, what does it mean to be very close? Well, once again, you need to define a notion of distance. And so even there, people toy a lot about with notions, okay, what it means to be close, right? In dimension 1, dimension 2, dimension 3, dimension 4. And so there are all kind of different metrics. And people wrote papers and got tenure based on ideas on how to metrize matching estimators, right? And here it will be kind of a similar idea. I don't think there is an obvious answer to that. It's not clear how to define what is close, right? So in this kind of setting. In one dimensional are these trivial because everything is scale invariant and everything is one dimension, but here all of a sudden these things can matter. Okay, any other questions?
So how do we, you said you have to think about the substantive questions you might have. So how do we factor in the target population we want to act on, think about, draw conclusions about, when we're choosing these distances? How do we, based on your own experience, how does that factor in?
Well, I must confess I have zero experience with practice. I'm a theoretician. So I did some empirical work long time ago that I can comment on. And nowadays I do empirical work for a private company that I cannot comment on. I have an NDA that prevents me from commenting on that. So I have never done practically. So maybe Juliana could answer that. I don't know. So I mean, my intuition here is that definitely you need to scale the variables because otherwise the notion of smoothing is very weird, right? So if you don't scale the variables, and I told you these units are 10 units of distance away from the boundary, what does this really mean, right? Because if one direction is metrized in units, I understand that, right? 10 blocks or $10, right? But then the other direction could be metrized in something that for which that 10 means nothing, right? So I don't really understand what that is. If you explain it to me in terms of standard deviations, at least I could understand that. I don't know how useful it is, but at least I could understand it. But I completely agree. So if you didn't pay attention to these small subtle things, you could basically be averaging essentially along the axis, right? Because that will be moving almost nothing in one direction and moving yourself in the other only because of the scale. Yeah. And that would be weird, right? Because you will be learning your treatment effect here. You will be learning your treatment effect here entirely from units that are in the axis direction and nothing else, right? And so that will be also weird. I don't know if that makes sense, right? So it depends on the scale, obviously. Yeah.
Thanks.
No, of course. I mean, here, as you can see, everything has been standardized. That's why the scales are both standardized. But in the original raw data, it wouldn't be. Yes. Okay. Awesome. Any other questions? Yes.
So should we, and I don't know if this is the right way to think of this, but I'm always thinking of like your choice in how you standardize these dimensions is a statement about the data generating process, right? About how you the relative importance you think of these things, the things you should be. I mean, I guess the relative importance is weights, which is separate. But like,
yeah, no, I don't think it's a statement per se about the data generating process so much, because ultimately the data generating process is a scale invariant, right? So ultimately, if I told you what the condition expectation of this difference given X is, you will understand that. And I don't need to rescale things to make you understand that. It's more about what is the data that you are using to learn about this. You see what I mean? Like, I mean, yeah, I don't think it's about the data generating process. I don't think that's what's going to matter. What matters is how you implement. It's about the estimator, not the estimand. If you, maybe that's another way to say it. It's how you implement things. So I guess what I'm trying to say is that when you move from one dimension to two dimensions, all of a sudden you have more tuning parameters than before, and you didn't pay attention to them, right? I guess that's another way. Before you thought, oh, I go from one dimension to two, I still need to choose a bandwidth. But in reality, it's not only the bandwidth, now it's also how you metrize distance in order to choose the bandwidth. So all of a sudden that matters. I guess that's the way to do it. I'm hesitant only because maybe you are way deeper and your question is more about when I choose a distance, that can change the properties of the estimator and by construction the estimand, and the answer is yes. So maybe that's what you're after. So if you're after that, I completely agree. So when I write this here, I don't know how many of you could even make sense of it, but actually it's a non-trivial task to make sense of this. Okay, so what does it mean to integrate a function multiplied by a density that doesn't really matter over a one-dimensional curve? So that notion has to be worked out. I mean, it's beyond the scope of today, but maybe that's what you're alluding to, right? So defining even this object properly is non-trivial, right? Because again, think about it. It kind of makes sense, right? So when you define an integral in one dimension or two, if you're integrating over the whole domain, that's not an issue. But now you're integrating over a very special domain. You're only integrating through the boundary. So you can imagine that if the boundary is super crazy, things could go wrong, right? So intuitively, I mean, if you think about integration, right? So it cannot be super crazy. This object here cannot be super crazy. So you need to kind of think about, is this boundary okay? Is this a more crazy boundary okay? And so again, so maybe if you're referring to that, you're absolutely correct. That matters quite a lot, actually. In fact, I can say more. I'll show you a little bit, but I mean, it's not the point of today, but justifying this arrow will require putting conditions on what the boundary looks like, and it will require putting conditions on how you do the distance metrizing as well. And those two are going to matter. And we have counterexamples. So we have examples where this convergence doesn't happen because either the boundary is too crazy or the distance is too crazy, one or the other, right? So, but for all intent and purposes, it's not a big deal. I think in practice, things work here for the most part, right? Yeah. But you need to restrict the bound. So that's a fact. Okay, good. Any other? Yes.
Is there the situations I often have, like a census block or like an information district, which is like a closed. It's not like just a boundary that kind of like we don't worry about the ends, but just like a unit, like a few blocks. Does that alter? I guess it has kinks in the way that like a square would have kinks, but does that the fact that it is a closed kind of unit alter anything? Or is that
Okay, so just to be clear, what you're saying is maybe we are estimating treatment effects where the boundary is like that, and so this is maybe A1, and everything here outside that is A0. Is that right? Is that what you're saying? Okay, so the treatment effect is still estimated along this guy here, right? So if you were to write the pooling approach in this context, it will look like this. So inside, it will be a rectangle, right? And then all the data in here, you're still seeing, that's good. Let's see how long it lasts. Your Zoom gets angry when I do a lot of plotting. So that area will be fine, right? So all the units in the red area will estimate the treatment side of things, no problem, along the boundary. On the outside, it will look like this. You will have these clasps, and then linear, and then curve, then linear, then curve, then linear, then curve, then linear. And then all this area will catch units in the control group that are sufficiently close, if you like. And then you're still estimating treatment effects aggregated along the boundary, like this. So that's not a problem, right? That's not a problem at all. Now, what is a problem, for example, is if you have a boundary like this, and then the boundary comes, and that's like this. Can you see why? Because again, it's kind of these geometries where it will be very, very hard to estimate something for this region or maybe for that region, right? Obviously. Can you see why, right? So those are regions that might get you into trouble. And so again, if you do geography, these kind of things could happen. So you have to pay a little bit more attention. I mean, again, you feed in data and the software is going to get you something back, right? But I mean, come on. You feed data and theta and R drops half of the data and then whatever remains uses, right? So, I mean, that's not the point. I mean, we need to think about what we're doing, right? So, yeah.
I guess I'm probably jumping the gun here, but solution to this would just be like drop those regions for which the I guess the integral can't be calculated.
Absolutely. So one solution is to change the estimate, right? And some people love that, including people who got Nobel Prizes. That joke is too specific unless you know the literature, but some people love to change the estimate, and that's perfectly fine. So if you grab, so let's go back to Juliana's application. So if you are concerned about what happens around the kink, you could, for example, estimate something in this region and then something in this region, right? And be done with it and never say anything about this region here. I mean, again, whether you like it or not, there is a tuning parameter going on here, which is that decides how close you get to the king, but putting that aside, you can definitely do that. That's perfectly fine, right? I mean, I think in your original paper, you kind of did that, no? You did one side and the other, right? Yeah, exactly, which is perfectly fine. There's nothing wrong with that approach, except that, of course, you don't learn anything about this region, right? So you're kind of regularizing the problem, right? In a sense, or changing the demand that you are targeting, and then that's fine.
That's fine as long as you don't think there's anything special about that specific.
Correct. But again, you are using the information of this problem because here there is a single king, and you maybe think, okay, well, those students are not that different than their students on the other side. But now if you are in geography, when you have a bunch of these kings, then how do you do that, right? How many of these regions you chop out, and how do you do it, and what you keep, what you don't keep? I mean, again, this is a very simple example on purpose, right? So in this simple example, it's fine. Yeah, very good. Any other questions? Okay, so let me finish the introduction, and then maybe we can take 10 minutes off, and then we can do the second half where I will show you a little bit of how to do this in practice. I'm going to skip most of the theory, but you can see something. The slides are all online, so you can download them if you want, or I can give you links for it. Okay, great. So as I was saying before, the idea now is that you can basically run regressions. I'm back to the idea of discretizing along the boundary and estimating treatment effects along the boundary. And you have two approaches to do that, right? So one approach is to first reduce the problem to one that uses distance. And so you run the regression like you would have done it in a classical RD design. You just regress the outcome on the treatment indicator and the interaction between the one-dimensional score, which is a distance now, to every 1 point, right? So, of course, if you change the point, you change the distance because you need to recompute it. And so you're going to compute distance 40 times, right? But for each time, I mean, nowadays with software, that's not a problem. So you compute it 40 times, you get 40 scores with their corresponding cutoffs, right? And the cutoffs are the distance to that particular point, B1, B2, B3, and so on. And then you run your one-dimensional object. Or you can go straight to 2 dimensions, right? So this is the idea that I was telling you before. This is kind of a little bit new because here you don't do the regression in 1 dimension, you do the regression in 2 dimensions, right? So you need to actually do a bivariate local polynomial regression. So you localize in a bivariate sense, and then you run the bivariate regression. And so without giving you a lot of details, what I want to plot you on the right is how these two approaches perform, right? And so this is B1, and this is B1 through B10, right? So the blue one in this example is the one that runs the bivariate, and the red one is the one that first computes the distance and then runs the univariate. So we're comparing the univariate approach versus the bivariate approach. And this is a simulation where I do 10,000 times the same thing and take an average. And so the target in this example is the black line. And so as you move yourself, you go down from B1 to B10, you see that the blue does very well in this example. The red starts doing well. At the beginning was not doing super well. That will be for reasons of boundary over there that I will discuss later, but it's not doing that bad. But then as you continue on, you keep going down. So now I do it up to B15. And then the red, the distance base, starts to do worse. It goes up, has more bias, right? And then if you continue on, you reach 21. So now I did 21 RD estimates, right? So either univariate or bivariate, multiple times for the simulations, and then I report the average. And then you can see that there is a little bit of a bump, if you like, that happens near the kink, right? And then if you keep going, you see that this bump happens on both sides of the kink, and then it disappears as you walk away from the kink, right? And so, again, this could be an artifact of the simulations, or it could be something deeper going on, okay? The intuition here is that there is something deeper going on, and that deeper thing is that these distance-based estimators could sometimes have a bias near kinks, okay? And so I'm going to show you where that is coming from, but just in a nutshell, it comes from the fact that you're going to be computing distance to the point, And that distance is gonna kind of not see the kink, and it's gonna get confused because of the kink. That's kind of the idea, so I'll show you in a little bit. And so from that perspective, there are settings where you would prefer to use the bivariate instead of the distance base, because it will have less bias for estimation. Okay, and so again, in the software, we provide both, and there are conditions under both work well. How big of a deal this is in practice is not clear, so we couldn't find a lot of applications that really exhibited this high bias. So in general, this distance-based approach seems to work well as well. Okay, very good. Excellent. And so to finalize, let me just mention, and then we'll take a break. If you're going to do estimation along the boundary, then you are estimating 40 treatment effects. They're tracing out this treatment effect curve, if you like, along the boundary. And so naturally, you would like to have uncertainty quantification, not only for each of the 40 treatment effects, but also for all of them together, right? And so this is the idea of confidence bands, where basically what you would like to do is to kind of construct a confidence region that works jointly for all 40 or 80 or 120 or whatever it is, a number of treatment effects that you used, that you estimated in over your mesh, your discretized points. Okay, and so I'll tell you a little bit about how this works, but it's not super important. It's kind of intuitive. You estimate each of those, then you put the joint distribution. They're all Gaussian, so you just put them all like a long vector, and then you construct the joint confidence bands accordingly that way. There are basically three main methodologies in this literature of boundary discontinuity science. Two methodologies, which are these ones, focus on estimating treatment effect heterogeneity along the boundary. Personally, I think it's the right way to think about this. First, you learn what the treatment effects are along the boundary, and then you aggregate them after. But in some cases, you might want to just do the aggregation to start with, and then you construct these kind of bands, and then you just do the treatment effect estimation along the within the bands, basically. Okay, very good. And so these are the three. This is the summary of the three methodologies. What is common to all three of them is that no matter what, we are reducing the problem to essentially a regression discontinuity design problem, meaning that either we localize along the boundary, and then we do an RD for each of those many localization points that you chose to use, or otherwise you first pull all the data, make it look like a RD, and then you literally go ahead and implement an RD design. So either way, this means that we need to learn a little bit about how to do regression discontinuity designs, and then we can port those ideas into this methodology or this problem that we are interested in. And so for that, what I'm going to do is I'm going to walk you quickly on some of the basic ideas for estimation and inference in RD designs. I'm only going to focus on the two things that I think are more important, most important when you port back to boundary discontinuity designs. Okay, so this will be a little detour of about 30 minutes or so, and then I'll show you, again, I will not cover everything here. I will just focus on 1 and 3 basically, and then the rest is for you guys to enjoy. I gave the links to all these to the coordinator, so you can get them from them. Okay, so I'm not going to spend much time here. So RD designs are well known to you. There is nothing fundamentally different between the classical one and point by point along the boundary, in a sense. The only thing that, of course, is very important, that is local. And so the localization in the classical RD setting boils down to learning something at the cutoff. The localization in the boundary discontinuity designs boils down to learning something along the boundary, right? And that's kind of the difference at the end of the day. So as you know, we need to have a score. In the context of boundary discontinuity designs, are distance to the cutoff at each point along the boundary or along the band. And then once you have that, you have an assignment rule depending on which side of either the cutoff or the boundary in the boundary discontinuity design you are on. There are a bunch of frameworks. This morning, I learned that I am already behind because I need to extend boundary discontinuity designs to fuzzy settings. So which is IV type of imperfect compliance settings. So I'll discuss those not today, but something I need to do. Okay, so what is the beauty and the curse of regression discontinuity designs? So just to put everybody on the same page, no matter how we define the treatment effect, right? No matter which treatment effect we look at or whether it's a curve or not, the natural contender is a randomized experiment, right? And so we need to think about what are the things that we learn in one case but not the other, and what are the differences between the two designs. And so here I set up the basic in both cases, so there are potential outcomes. In the case of randomized experiments, the treatment assignment is independent of everything. So in that sense, the assignment mechanism is exogenous, if you like. And then the observed data is nonetheless the usual causal inference type or switching model or potential outcomes setup. And then here, what we call the average treatment effect is the expectation of the difference of potential outcomes, right? So intuitively, what it means is that if I were to grab every unit and move it from control to treatment status, what would be the change in their average outcome as a result, right? And so in randomized experiments, we estimate that by computing difference in means, for example, for each of the two groups. And so when you go to RD design, the key difference, and here I give you some movement with my finger, you can see that what the changes really are. So the most important change in RD designs is that the assignment mechanism has changed completely. So we go from something that is exogenous and random, if you like, to something that in a sense is no longer exogenous or random in the sense that it's completely deterministic, right? So once you know where you land relative to the cutoff, and again, in the boundary discontinuity design, there is no difference. So the cutoff changes along the boundary, and therefore the distance does, but ultimately it's the same idea. You deterministically change status from one to the other, right? And so there is this notion of common support that is broken in RD designs because all units on one side of the cutoff are assigned to one group, all the units on the other side are assigned to a different group. And so that poses the problem that all we can learn is a different parameter, and the parameter that we can learn is the average treatment effect for those units that happen to have that value of the score at the cutoff, right? And so going back to the boundary design, if you like, which is kind of what we've been talking about, is this idea that all we can learn really is the treatment effect for B1 or the treatment effect for B10, and all these are literally treatment effects along the boundary. So we will not be able to learn things outside the boundary unless we put substantially more conditions. Okay, very good. And so the way to formalize this idea is by basically saying that we are estimating the difference of average response of units when you come from one side or the other of the cutoff, right? And so in the one-dimensional world, coming from one side or the other is trivial because it's a scalar, so you're just coming along the axis of the score, univariate score. When you think of boundaries, now things get more interesting because coming from one side or the other, well, you can come from very different directions, right? So you can come from this direction, you can come from that direction, you can come from that direction. And so, again, it goes back to the idea of metrizing, right? So what it means to be close to B10, it depends on how you measure distance to B10, whether you standardize the data, well, I mean, all these things start to matter all of the sudden, right? So when you do a smoothing, when you try to borrow information from nearby units to learn something about what happened at the cutoff, then smoothing now is going to be intimately related on how you metrize distance to that point. And this is a big change relative to the traditional RD designs. In the traditional RD designs, it's quite simple. When you smooth or you learn from borrowing information from nearby units, it's very simple to say what the nearby units are, right? And it's easy to interpret, at least. Okay, so here's a prototypical description of the RD design, which of course extends naturally to boundary designs as well, either thinking of them as the band, where you pull, or the heterogeneous treatment effects along the boundary. Ultimately, what you're doing is you're estimating the change in the conditional average response, conditional on being very close to the cutoff on either side, right? And so here the main challenge is, of course, one that says the blue line is identifiable from the data. These are units that are near the cutoff on the side of assigned to control. I can look at their average responses, take an average, and learn what the effects are along this curve. But then the moment I hit the cutoff, the moment I hit the boundary, I change assignment, and all I see now is the average response of units that are assigned to treatment. So that means that I have to impose an assumption that is fundamentally untestable, right? The assumption meaning that for units that are right at the cutoff but on the left, had they been right at the cutoff on the right but not received treatment, then their response is roughly the response I see, right? So in other words, what I should see is that there is some sort of a smoothness or continuity at the cutoff, right? Things should not change abruptly. And this is very easy to interpret in both traditional RD designs and boundary discontinuity designs. In both cases, what we are appealing to is the idea that there is no systematic manipulation or sorting of units around the cutoff, right? So if the units had the possibility of systematically changing their assignment around the cutoff, then naturally you will see units that benefit maybe from the treatment the most on the treatment assignment group, and those that benefit the least on the control assignment group. And so at that point, discontinuity breaks down, right? And in the context of geographic or boundary discontinuity designs, that type of situation could be even worse, right? Because in geography in particular, it's quite common to see units sorting around these boundaries, right? And so it's kind of a challenge, I think. I mean, I've seen hundreds of geographic-based RD designs in empirical work where the authors don't even try to justify validity of the design, right? So I think it's very, very important to always think to what extent units are really unable to manipulate along the geographic boundaries or any other boundary for these matters, right? So in this case, the question will boil down to where the households able to manipulate their poverty index, or where somehow able to systematically manipulate their scores on the exams, exit exams. Okay, okay, very good. So in the absence of such manipulation, then you can take the average response of units on the left of the cutoff as good counterfactuals of what would have been the average response of units to the right of the cutoff in the absence of treatment, right? So that continuity allows you to think about that. And now all of a sudden we can do some estimation, right? So estimation means that you would like to learn the value of the function here, the value of the function here, and then compute the difference between the two, okay? And so that immediately lands in the world of local smoothing, right? So we don't really want to learn the function here or here. All we want to do is to learn the functions near the cutoff, right? So naturally, if we could, we would estimate the effects right at the cutoff, but of course the score is continuous, so you're not gonna have more than one, most likely zero observations at the cutoff, so we need to borrow information from nearby units, right? And that's at the core of any regression discontinuity design. This is a fundamental difference from parametric analysis, whether you like it or not. You are borrowing information from nearby units, right? And whenever you borrow information in the form of local smoothing, you are effectively trading off bias and variance, right? So why is that? Well, because if I borrow more information, I'm forced to go myself farther away from the cutoff to be able to borrow from more units, more data that I see. But the more I move away from the cutoff, the less likely my parametric specification will be right. Okay, so I have this trade-off where if I enlarge the region where I'm doing estimation, I will decrease variability because I have more information. I'm borrowing more from nearby units at the price of injecting more bias, more misspecification bias, right? And on the other hand, if I shrink my region, if I zoom in to the cutoff, I start losing information because I have less units to rely on. But then hopefully the ones I have are going to be better reflections of what the average is at the cutoff, right? And so there is this natural trade-off of bias and variance, and we need to somehow trade that off, right? And now here is where a big distinction happens, and unfortunately, I must confess a mistake that we even made in some early recommendations, right? Why is that? Well, because think about it. When we are smoothing in one dimension, as we move ourselves away from the cutoff, we add observations, right? And the probability of adding observations is equal to the distance that the observations have. So roughly it's 1/n, if you like, right? But when you move from one dimension to 2 dimensions, then all of a sudden you can increase a little bit and still not catch observations, right? Because the same data will be spread out more on space in 2 dimensions that they will be spread in 1 dimension, right? So this is a well-known phenomenon. It's known as the curse of dimensionality. That's why as you have more data, more dimensions, non-parametric estimation is harder. It's no easier, right? It's harder, right? And so the reason for that is because for the same data, now in 2 dimensions, now the data is more spread out in some sense, right? And so that affects how the estimators behave. And so intuitively, or unfortunately, it's not obvious that whatever was true in 1 dimension will immediately translate in 2 dimensions, right? Because, for example, selecting the optimal smoothing, the optimal region for estimation in 1 dimension might not be the same as in 2 dimensions, right? So you need to change something. And this could be quite worrisome. Why is that? Because, and this was our mistake, you can grab your boundary discontinuity design, choose a boundary point, B5, and then immediately compute the distance, the univariate distance of every data to that point. And then grab that univariate distance, which is a scalar, and the outcome, which is Y, and then pass that to the software in 1-dimensional RD. And the software, well, of course, I mean, it's written by us, so it's fantastic, but it's not that fantastic. It's not an oracle. I mean, it doesn't have the crystal ball yet. So it doesn't really know that this data is artificially 1 dimension, but in reality, it's a 2-dimensional data, right? I mean, unfortunately, all what the software sees is a column of distance with cutoff 0, right? Because 0 distance means that the cutoff, greater than 0 means away from the cutoff. And so all it sees is distance, right? And so it acts as if it's a 1-dimensional RD, but in reality it's not. It's a 2-dimensional RD that has been shrunk artificially to a 1-dimensional RD. And so at that point, bandwidth selection will not be correct, okay? I mean, you can still use it maybe, that's a question to ask, but ultimately it's not immediately obvious that just by reducing the problem from 2 dimension to 1 dimension and then using 1-dimensional methods, that then you're going to be fine, right? So you need to actually explore and understand to what extent that is the case. And it turns out, as you will see in a minute, that if you were to reduce the 2-dimensional problem to a 1-dimensional problem artificially by measuring as distance to the point and then passing it on to a software that is 1-dimensional in nature, that software will execute a bandwidth selection that turns out to be too small, okay? So in the language of non-parametrics, that is known as under-smoothing. It's going to choose a bandwidth that is too small. It's a bandwidth that would not take into account the fact that because the data is truly 2-dimensional, you actually have more variability than you thought you did, right? So in some sense, I guess this is another way to think about it intuitively. You're grabbing a 2-dimensional problem, shrinking it to 1-dimensional problem, and now the software thinks it's 1-dimensional, and therefore thinks that you have less variability than you really have, right? And so because of that, it will choose a bandwidth that is smaller than it should be, right? And that is a problem. So UCLA internet sucks. I don't know how to put that in a way that is not offensive, so I apologize. I wish I had a better way to say it, like more politely, like maybe, oh, UCLA is facing challenges with their internet. Okay, let's try again. Okay, so the main message here is that, again, you have to think. And I know that that's not what people often like, but it's important to think. You know, it's kind of cool. You think, you learn, you do good stuff. So in this context, it means that we need to understand what are the implications of using perhaps an incorrect bandwidth by virtue of relying on a 1-dimensional approach, when in reality, we should have used a 2-dimensional approach, right? And again, you already kind of know the answer to that a little bit, right? Because as you know, if you choose a bandwidth that is too small, you have too few data points relative to what it would have been optimal, and that implies that you're going to have less bias, but more bias, right? So you have more variability, so your thing is going to be jumping all over the place, right? And so ideally, you would like to correct that. right? And so if you have a good understanding of how things work, then hopefully you can correct that, and then that will help you. Okay, so I'll talk about that a little bit, but in order to do so, I need to first walk you through what you are really doing in one dimensions, right? And once we know what you're doing in one dimensions, I can tell you exactly how it's done in 2 dimensions, and then we're going to be in business to implement the methods for practice. Okay, so in order to do that, let me quickly show you all this doesn't matter today. So let me skip this part too. There we go. Perfect. So we're here. Let me now tell you how people do this in practice, and then we're going to practice quickly on understanding what the changes are. And again, for today, think of this not so much as a review of classical RD designs, but more as a contrast on where things change when you go to boundary discontinuity designs. Okay? So the way that we're going to do this, as I said before, is we're going to localize, right? And this happens both in 1 dimension, 2 dimensions, or so many dimensions that you care about, because all the identification comes from shifts in treatment assignment at the cutoff, right? Or at the boundary. So we need to localize no matter what. And so the way that we're going to do it is we're going to follow this recipe or this approach. This approach is not the only way to do things, but it's the one that most of the time people do in practice, right? And so we're going to follow practice in this sense. So the way that it's going to be is we're going to localize, and localization is going to be controlled by the bandwidth, the region that which determines the region for estimation. And so in order to do that, we're going to make some choices, right? So the first choice that we're going to make is we're going to choose which polynomial approximation we're going to use. So this is purely a modeling device. So typically in practice, you use linear regression. So I'm happy with linear regression, in which case P is equal to 1, right? So you just run a linear regression local to the point of interest, in this case, the cutoff. And then you're going to choose sometimes weights. So for most of what I discussed today, I didn't even mention the weights, but sometimes people like to downweight observations as you move away from the cutoff. That will introduce some good and bad things. In practice, often people are happy with using the uniform weight or the uniform kernel. So that would say within the range of estimation determined by the bandwidth, you can give equal weight to all the observations. So literally run the regression. That's what it's saying, right? Otherwise, you run a weighted least squares regression, but it's the same idea. Okay, where things get a little bit interesting is how you choose the bandwidth, right? And so as I told you before, the way that is often done in practice is try to take away from the researcher arbitrary choices, and so try to do something that is data-driven, at least as a benchmark point, and then you can play with it. And so the most common option is to choose the MSE optimal or mean square error optimal bandwidth choice. So mean square error, if you don't recall this from your classes in statistics, is nothing more than the variance of the estimator plus the bias of the estimator square, right? If your estimator was unbiased, then we will have no problem, right? You will just run least squares and everything will be nice and you will estimate things. The crux of the argument here is that we believe that regression discontinuity or boundary discontinuity designs are all fundamentally misspecified problems, right? So all we can do is try to approximate these regression functions near the cutoff, and ultimately we are introducing a bias no matter what. If you don't believe that, then you don't need any of this because your model is correct, right? So you're in really good shape. But in most applications, and most people would believe that those are just approximations, and you would like to kind of quantify those approximations. And so the way that we quantify them is by moving the region of approximation and trying to understand whether we are injecting more bias or less bias, right? That's kind of the idea. So let me show you a couple of pictures, and then I'll come back to this. So here is how we do it. We choose a cutoff, or we have a cutoff. Then you catch data up to H, and then you run the regression on each side, and then you look at the jump at the cutoff, right? That's the way that regression works. So let me show you a picture. It's worth 1,000 words. So this is the underlying regression functions that we don't know about. What we know is the data underlying them, right? So let me take out those regressions. I just stay with the data. And so what a regression discontinuity design would do, or a boundary discontinuity design at each point on the grid, or if you can think of this, it could be the band, right? So this could be distance, perpendicular distance to the manifold, to the one-dimensional boundary, right? And this will be exactly the same thing. Of course, that will be interesting because each of these points will be perpendicular distance to some point on the boundary. we don't know where, right? Okay, good. So what do? You first choose a bandwidth, and the bandwidth drops everything that is outside the region of estimation. So we're localizing, that's key. So this is the localization region, the neighborhood region that we really care about. And then we're going to try to estimate the regression function that lives underlying these regions, right? And so we're going to do it by fitting a polynomial, a linear regression. So this is the simplest possible case. And now you can see what happens, right? So as I move my H in, out, or in, I'm adding or subtracting data, right? So if I move it a little bit to the left, then I'm adding more data, and therefore my fit changes. And it changes in two ways. I have more data, so my fit is going to be more precise because I have more information. That's where I borrow information. But I'm also going to have, everything else equal, more bias, right? Because my linear approximation will get no better, possibly worse, as I enlarge the region where I use it, right? The same way, if I move my bandwidth in, now I drop data, right? And that dropping of data injects more variability. I have less information to rely on, so my uncertainty increases, but my linear specification will get no worse, hopefully better, right? So it will be a better approximation for what the function is at the cutoff. And so you can see exactly the trade-off, right? So the trade-off is, if I enlarge the bandwidth, I reduce variability, but I increase bias. If I shrink the bandwidth, I increase variability, but I reduce the bias. So the mean square error is a beautiful quadratic that we can find an optimal for, right? So we can find the optimal choice of H that trades off my misspecification error, given the choice of polynomial order, weights, and so on, and also trades off against the uncertainty of my estimates. And that's exactly how we do it in practice, right? So in practice, if you have used any of the empirical or the packages that are out there, I mean, the good ones at least, they should grab the data, learn a little bit about what this variability, how the variability changes, and how the misspecification error changes as you vary the bandwidth, and then we'll find the optimal bandwidth that kind of trades those two off, right? That's the idea. Okay. Excellent. And so here you can see exactly the graphical representation, right? So this is the one choice of bandwidth. This is a misspecification error. That's the misspecification error, right? And so one question that I get often is, well, how do you do it in practice? Because we don't see blue, we don't see red. All we see are the dots and the black lines. So how do you actually learn what the misspecification error is, right? Okay. So I'll tell you what the secret sauce is, so you know a little bit. So it's not very hard, right? So if you try to learn the misspecification error, a very simple way to do it is to compare different models, because different models could have different misspecification errors. And if you know which one has largest or the smaller misspecification error, then in a sense, you can difference them out, right? So you can kind of learn, oh, if I go from one model to the other and my misspecification error goes down, then the difference of the models will tell me what the misspecification error was, right? That's kind of the idea. Okay, that's exactly what we do. So what we do in the software is we run a linear regression, which is the one that you see, right? But also in the background, we run a quadratic regression. In the quadratic regression, it's very interesting model, it's very unique in this sense, because, not by chance, but matter today, but it's nested, right? Because you run the linear model and then you add the quadratic. And now all of a sudden, the second model is flexible, but nests the first. So if I look at the quadratic coefficient, it's an estimate of how much misspecification error I had. Can you see that? It's kind of obvious, right? Because if the model was linear, then when I add the quadratic is going to be estimated as 0. So it will be 0 misspecification error, residual misspecification error. But if the linear had misspecification error left off, when I fit the quadratic, it kind of gives me a sense of how large that was, right? And that's exactly what we do. We run a linear regression, then we run a quadratic regression, and then we look at the quadratic coefficient. If the quadratic coefficient is very large, you have a lot of bias. If the quadratic coefficient is very small, you have no bias, no misspecification bias, right? And, well, the coefficient gives you the notion of misspecification. That's exactly what we use. So we grab that thing and we properly massage it, and then you get an estimate of what the misspecification error is. And that will give you a sense of what the misspecification error was for your linear model, right? When you go from linear to quadratic. And then how do you capture the variance part? Well, that's easy, right? Because now you can see what happens, right? So I can look at the variability of this estimate, then I can look at the variability of the larger model, and then again, I can see about how much the variability changes, right? Or we can use one of those as an estimate of variability, and that's what we do, right? So in a sense, we estimate the variability, we estimate the misspecification error, and then we trade off the two. And once you trade off the two, you can choose the balance, right? And again, in a classical one-dimensional RD, this theory, I mean, this methodology has been well developed. There is nothing new at this point. But now the question is, if I was to deploy this methodology to boundary discontinuity designs, which portions will be correct and which portions will have to be adapted, right? That's kind of the notion. Okay, excellent. So here's an example of how misspecification works. So in this case, I'm going to show you how the bandwidth affects misspecification. So this is a large bandwidth. You can see that the linear fit tries to approximate a nonlinear blue. The linear fit tries to approximate a nonlinear red. If you were to shrink the bandwidth, now a linear approximation actually does a much better job, and a linear approximation does a much better job, right? So a smaller bandwidth shrinks misspecification errors, larger bandwidth increased, right? That's a very simple, intuitive idea. Okay, excellent. And so how do we do this? Well, I already told you the answer to that. So we're going to choose a bandwidth that is optimal in mean square error. It's going to be trading off variance and bias square, right? Up to some massaging, which doesn't matter today. And then you're going to estimate these two, and you're going to plug it in this formula, and then you're going to multiply it by n to the minus 1/5. Okay, and the n to the minus 1/5 comes out of how this estimator behaves, and it traces off bias and variance in the right way, okay? And here is where things break down, okay? So this formula works when the model is univariate. If the model is bivariate in nature, even though you artificially made it univariate, then this formula will be wrong. And actually the right formula that you should be using, paradoxically, is very simple to fix. You have to cross out this 5 and put a 7, cross out this 5 and put a 7. And then you're in business, okay? It's very, very easy. So, very easy. Yeah, I'm not joking. It's just like that. I mean, also, you need to adjust this constant, but that's not that important. Okay, so bottom line is that if you were to artificially make it one dimension and deploy the software for one-dimensional problems, you will be choosing a bandwidth that is going to zero faster than it should have been, right? And so because the bandwidth is going to zero faster, so well, let me help you out, right? So as I make the exponent on 1/n smaller, right, it will decrease to zero slower, right? And so, okay, good. So this choice of bandwidth is larger. Can you see that? It should have been larger. So it should have been a larger bandwidth. It should go to zero slower than the bandwidth for one dimension, right? And the intuition here is because you artificially make the software believe that your problem is univariate, but in reality it's bivariate. So you have more uncertainty than you thought, okay? And so that changes the bandwidth. And the bandwidth changes the estimator, right? Because now the region that I used to estimate changes, right? So now the whole point estimation changes and everything changes along the way, right? And so we have to be careful how we do that. Now, the good news is that this bandwidth is, sorry, not this. The bandwidth that comes out from the naive plugin is n to the 1/5, as opposed to, let me call it 1/7 and 1/7. So the 1/5 bandwidth, which is a one-dimensional bandwidth, will be smaller than the optimal bandwidth, right? And here is something that at least some people will be happy about. I'm not, but some people would, which is that the error of hitting the wrong bandwidth is not symmetric, right? So if you choose a bandwidth that is smaller than optimal, you're going to have an estimator that has less bias but more variance. And some people are happy with that. Why? Because well, the asymmetry of type 1 and type 2 error, I suppose, right? So you don't want to have false discoveries. And so you would like to have something that has less bias, even though it's more precise. It's less precise, right? So it's more uncertain. And so people tend to prefer more uncertain, less biased estimators than more precise, but also more biased estimators, right? Because of false discoveries. And so for that reason alone, some people are okay with plugging in these wrong bandwidths, right? So in practice, nothing is going to be wrong. It's just that you're not using an optimal point estimator. You're using something that is too variable and with less bias than optimal. Okay, very good. So here is the trade-offs that I already explained. And so in practice, I'm not going to go through the whole theory, but if you were to do it, the mean square error would have had to be of order n to the minus 1/7. Okay, and so if you are interested in the math, you will see mean square error expansions that have bias and variance, and then trade off to get the optimal choice. Okay, perfect. So we're gonna play a little bit with that and see how this works. Okay, and then the final piece of the puzzle in the last 5-10 minutes, and then we'll do some applications to play with this all, is the idea that after you did the optimal choice of the bandwidth, you need to tell me how to do inference, right? And so here's where things get a little bit tricky, because when you choose your bandwidth, you have this unfortunate phenomena that by choosing your bandwidth optimally, you're actually preserving bias, misspecification bias, in your distributional approximation, right? And so you cannot directly rely on the usual point estimator plus minus 2 times standard errors, because that will be wrong, okay? So you need to somehow make sure that there is no residual misspecification error when you're forming your inference procedure, right? And so there are multiple ways to do that. And the one that we propose in this line of work is to say, well, a simple way to do this is to grab your estimator, debias it, and then adjust the standard errors accordingly. Okay, so that's the simplest possible way. And one of the reasons why this one is simple and easy is because this guy you already had. In order to estimate the bandwidth, you actually had estimated this already. Remember? So I said you run a linear regression, then you run a quadratic regression. Oh, wow, but I already have my quadratic regression. So why don't I use it and then fix the bias with that? And that's exactly what we do in the package, actually. So we grab, basically, the whole package is a 3-line code. You run a linear regression, then you run a quadratic regression, and then you play with the different coefficients in the right place. And that's it. That's all you have to do. So it's a 3-line kind of code, except for other more subtle things. And then at the end of the day, you just form your estimate by running a quadratic regression and using the standard error from the quadratic fit. Okay, and actually this is a good point to pause, because again, we have software that people use, but actually you can do it yourself. So you can literally run the linear regression, you can run the quadratic regression, and then if you extract the right things in the right place, then you're in business. You can just do it yourself. Okay, excellent. I'm gonna skip on this. Okay, and so now, yes. I have not, and the reason is because it takes time and I'm impatient. So I use typically analytic standard errors here, but other people have continued our work and have shown that you can actually rely on the bootstrap, and you can either bootstrap this statistic altogether, or you can just bootstrap. I mean, I don't know your background, but if you use Stata, in Stata it's quite common that they use the bootstrap wrong, and they only bootstrap the point estimator to construct standard errors, right? Which is kind of the worst possible thing that you can do for the bootstrap. But okay, so you can actually bootstrap this guy and construct the standard errors, right? And then that will work too. So that has been shown to work as well. So you don't even need to compute these guys, right? So you know what I mean, right? So you resample the data, you re-estimate the quadratic fit, and then you compute the standard error of the multiple fits, basically. And that will give you this number here. I mean, not this number, but an approximation of that number. Yeah, so you can do that. But we don't have that implemented. I mean, it will be trivial in Stata, right? Because Stata recycles so you can just run it with a nested command, and it will work out for sure. Yeah. Okay. Good, excellent. Any other questions? Okay, so let me show you a quick introduction on how this works in the classical RD setting, and then I'm going to show you how it works in the boundary discontinuity design. So first, I'm going to do a very simple classical RD that I often use for teaching and for demonstration. So this is an RD design where you have a poverty index at the county level, you have a cutoff at this number, right? And then you have an outcome, which in this case is child mortality, not super important. And then you have some treatment, which is an anti-poverty program that was given to every county, or let's pretend that it was given to every county that exceeded their poverty index above that number. Okay, so that's kind of the idea. And so let me show you a little bit on how this works. And so I'll show you a couple of oh, there we go. Perfect. So I'll show you a couple of pictures on these. And so you can see the kind of pictures that come out from this. And then we're going to link them to. I'm using R today. I don't know why. I guess I know because other stuff is not. But okay, good. So here I'm generating all the variables for this. Oh, this is very small, by the way. Let me make it a little bit bigger if I know how. Right. A crude way to make it bigger. Control plus? Oh, wow. Control plus works. That's great. Good, good. Thank you. Okay. Okay, very good. So, okay, great. So now, let me show you how this picture kind of works here. Okay. Okay, that looks very small. Let me try to make it a little bit bigger. Okay, excellent. So I always use this picture to demonstrate one phenomena that I think is super cool and important to think about. So the phenomena is, great. The phenomenon is right here, right? So if you can see this is kind of a no-no, right? So this is one of the other things that keep me at night awake, because when you write software, you need to choose defaults. And somehow people think that when you choose defaults, that's like the gospel, right? Like people just go with that and say, oh, wow, it's in the software, so we should do it. No, you have to think. You have to use okay, look at this. Obviously, something here is kind of crazy, right? So you can see that it kind of fits a fourth order polynomial. It kind of stabilizes in the middle, but it kind of does horribly on the ends. Can you see that? Okay, that's a very well-known phenomena in mathematics. It's called the Runge phenomena. Actually, it's so well-known that at the beginning of last century, it led to the creation of new functions, including something that is called splines. Okay, and the basic phenomena says that if you try to fit a polynomial approximation to a function on a compact support, the polynomial approximation does well in the middle, but it does really, really bad on the edges, right? And in the edges is exactly what we care about, because the edges are exactly where we're trying to understand what's going on. So that's why you should never use, and this I can say confident, you should never use global polynomials for RD, right? So that's a really bad idea. I mean, graphically, you can put it, it looks nice, whatever, but conceptually, it's a really bad way of approximating functions. And it makes sense, because think about it. The polynomial is going to try to approximate the function, but the coefficient of variation, how much the function varies, it will be highly affected by this point here, right? So if you push this point down, the polynomial is going to try to fit that point, so it's going to push down in the tail or in the string, and then it's going to stabilize itself in the middle. And so that's a really bad way to go forward, right? And so you can open Wikipedia and see this. I mean, in Wikipedia, you have the Runge phenomena. It's kind of bad, right? So it's not a good thing. So we don't want to do that. We want to localize, right? So the idea is that we localize, we only work with the data that is near the cutoff, and then we do a low order polynomial fit, like a one, I mean, p equal to 1 or something like that. Okay, great. So here is, if you're interested, right? So it has even the pictures. Look at this. So you can even look at the picture in Wikipedia. It's like, it's crazy, right? So look at this right there, right? So you can see how the polynomials do horribly on the tail, and do okay in the middle, right? So you don't want to do that. That's a really bad idea. So don't do that. Okay, excellent. So now that we settled that one, what do you do instead? Well, you have to regularize. This is the idea of regularization, right? So all the time, we would like to be very flexible. We would like to put all the covariates that we can. We would like to put all the powers that we can. But at some point, you need to regularize. You need to somehow trade off bias and variance in a way that is meaningful to you. And so this is an example where obviously this needs to be regularized, right? And so one way to regularize is brute force. So what we can do is to literally fit a lower order polynomial, right? So if you fit a lower order polynomial, in this case, a local linear, right? So linear regression, then obviously this point will not affect as much the fit at the boundary as the fourth order did, right? And so that's kind of cool, right? So I think that's super important, right? So we go from this to that, right? Can you see that? Let me try to do it. I don't know how to do it. There we go. That's cool, right? Like this, like that. It's like movement. Okay, so we don't want that, right? But then again, if we fit a linear, we want to localize because otherwise the bias could be too large, right? So maybe we want to do it only in the region of whatever many points, and that's where the bandwidth comes in, right? But you kind of see what we're doing, right? So it's kind of simple. Okay, great, excellent. Cool. Okay, great. So now I was telling you how we actually fit this. Well, one possibility is to choose a bandwidth by hand, right? And so I told you this before. So we can choose, for example, -9 to 9, so 51 to, or whatever, 9 points up, 9 points down, right? So if we do that, then we can actually fit this in that region, right? So, I mean, I don't know if in R it works, but we should have the subset there as well, but I don't remember. Okay, good. So let me just show you how this will be fit in R, for example. So now I need to increase this. Perfect. And then okay, nice. So in the least squares regression, I mean, I hope you remember a little bit R, or otherwise I'll walk you through it. We're running the regression, right? And so then the thing that we care about is the interaction between treatment and being above the cutoff, right? So basically this coefficient here, and so this is like the jump. So this is this jump here, but only using the data that is -9, So basically is this with a bandwidth by hand of -9, right? And that's exactly what RD would do, right? And so this is also true in boundary discontinuity designs. You will position yourself at each point on the boundary, or you would do it on the band, and then this determines the band. And now once you do that, you can run the regression, right? And then all of a sudden, you are in business, right? And so here, very important, very important, we run the regression on intercept, treatment, which is what we care about, and then we put the linear score, and we interact the linear score with the treatment. This is very important. So there are tons of papers that don't do that, and that's really bad, right? Because that means that, for example, you have assumed the same slope on the left and the same slope on the right, right? And that's something that we don't want to do because a priori it's not obvious that it's correct. So we would like to allow for different slopes on the left and on the right. Okay? And there are tons of examples where that you wouldn't know how many papers we downloaded, replication files, and then we had to delete them because they forgot the interaction, and then when you put it, all the results go away. You know, like it's pretty, it's like a zoo out there. Okay, good. So then after we do that, now the question is how you do it with software. So I'm gonna give you one example with software. So just one, so you can see. So this is using our package for one dimension, okay? And so here, I'll show you a little bit of the changes, and now you're gonna understand most of them, and this is gonna be important for what comes next. So we have the data. So now here it says that we have chosen the bandwidth to be mean square error optimal. So now you know what that means, right? So somehow we approximated bias and variance. And then we use a formula that says variance over bias squared to the power 1/5 times n to the minus 1/5. N, in this case, is this number here. That's exactly what the software does. The software grabs this number, takes power minus 1/5, then multiply by the constant that estimates from the data, and get back this number here, 6.810, right? So that bandwidth here, this bandwidth is chosen exactly in that way, right? So if you go through the code, everything's open source, then you can directly choose this bandwidth here. And then if you want to decode the rest of the things here, now all of them make sense to you, I hope, or most of them. The first one says what bandwidth you use, mean square error. The second is what weights you decided to use. In this case, we're using triangular weights. That means that you are down weighting as you move away from the cutoff, you give less weight to the data. Or we could use uniform, that's fine. Variance estimation is done using some nearest neighbor matching, which is not super important. And then here's the total data on each side of the cutoff, right? So this is the data to the left, this is the data to the right. And now when you go down, you have, this is very important, this is the effective number of observations, right? So the effective number of observations is literally, once you chose the bandwidth, how much data was caught in that region, right? So the bandwidth was 6.8, 110, 10, and so we caught 234 observations out of 2,489, right? And these are specifically the 234 closest observations to the cutoff on the left. And then on the same, on the right, 180, okay? And now here comes the sauce, right? So P is the order of polynomial that we use for estimation. So that is the linear fit. But Q is the order of polynomial that we use to learn the misspecification error, right? And so as I told you before, to construct the bandwidth and to do bias correction, we need to learn how much misspecification error you have left, right? And so you chose to use linear regression, and then you are learning misspecification from running quadratic regression. That's literally what we're doing. We're extracting the coefficient from a quadratic, okay? The rest is not super important, and it can be all set to be equal to this number, so that's not a problem. This is a huge problem that people often miss, which is the idea that you don't always have unique data points, right? So many times you have mass points, and that kind of matters a lot, but not in this application, so I'm going to skip. Okay, and so now when you try to read...
Sorry, I think I missed that part. What does that mean?
Oh, very important, yes. So this is when you don't have unique values in your score. I should explain this. This is very important. It's something that we try to write about, but it's always exhausting. Okay, so this is very, very important. Suppose that you run an RD, right? And the RD has an N of 1 million observations. So that will be 1.
I don't think I'm seeing what you're saying.
0. Oh, that's completely right. Now you should. Yeah. Perfect. Okay, so you have 1 million observations, right? But it could happen that your Xi actually takes on 3 values, -1, 0, and 1. So that means that you really have -1, 0, and 1. And then your 1 million observations actually happen to be all lined up along these 3 values, right? So really, you don't have 1 million observations for learning the curvature or for learning the regression function. You only have really 3 values. You have -1, 0, and 1, right? So in other words, when the score is not continuously distributed, when the score has mass points, you don't really have the observations that you thought you have to learn the features that you are interested in, right? Obviously, you can barely learn a linear function from this, and you could not learn a quadratic, right? Because you only have 2 unique values in X, right? So you cannot learn the quadratic. I mean, on the left, you cannot even learn the linear. You cannot, right? All you can learn is the average at that point. So, okay. So that refers to how much how many mass points or unique values you have in the score, right? And so in this application, you can check this number against this number, and this number against this number. And because it's a poverty index, actually, in this application, in this direction, you are continuously distributed, right? So every unit has a unique value of poverty, right? So that's great. In your application, one dimension is continuously distributed for the most part. The other dimension is not, because the other dimension only has 100 values, right? Ranks. And so by construction, you can have 350,000 observations, but in reality, you only have 100 rank points, right? So you only have 100 math points. In the other direction, you're going to have very much continuously distributed X, right? So, and again, that begs for you to think about what it means to estimate a regression function, what it means to approximate the curvature of a regression function, and things like that, when you have very few unique points. So a typical example that you will see on this, maybe you have seen it if you follow, what am I doing? There we go. No, there we go. Here, a typical example that you might have seen is Medicare, right? So that's a typical example. So people have access to the census and they claim to have millions of observations, but then they look at the effect of Medicare in terms of their years. So you have 65, 66, 67, 68, and then you have 64, 63, 62. And you even see the plots. When you see the plots in these papers, you often see that they have really a bunch of vertical lines, and they only have effectively 10 points of variation in the score. And variation in the score is what gets you learning of the condition expectation, right? So that's very important. That's something to always pay attention to. Okay, good. Okay, so just to finish this quick demonstration. So then when you come to the output, what you do is you look at the point estimate. So the point estimate will be the treatment effect, just like in that picture, local, in this case, local to this bandwidth, right? And then this point estimate will be computed using P equal to 1, linear regression, and this bandwidth here. But then when you go to inference, you actually compute it using a quadratic fit and the corresponding variance of the quadratic fit, right? And so then for that choice, with this same data, then you are in business and you can construct your confidence intervals here. Okay, so that's kind of what we do. Any questions so far? Okay, excellent. So now we can link all these to the case of boundary discontinuity designs. And so what I'm going to show you now is a little bit of an application on how to actually do this, how to construct these treatment effects, these confidence bands, and everything else. So the confidence bands require simulation, so it will take a little bit longer. So I might not show you that, but I'm going to show you at least some of the point estimates and how they are constructed and so on. Okay, excellent. So for that, let me go to the empirical application. And so this is the empirical application from Juliana, who I already introduced a little bit. And so now I'm going to try to replicate these pictures for you, right? So the same idea as before. So now we have two scores. We have Saber 11, which is this exit exam. And then we have the poverty index, which is on the y-axis. And then you can see here that we have two types of plots. You can have the scatter plot of the data on the plane along with the boundary. And then you can have, of course, the point estimates along the boundary, right? So again, just to remind you, this B1 is this B1, right? And so here, what we are really plotting is essentially, I mean, I'm going to do my best now, but it's going to be not great. So bear with me. So if the boundary looks like this, what you're really trying to plot is this, and then there is a function here, and then there is another function here, right? And maybe that's something like that, like this. Okay, that's my best attempt for 3D plotting. I mean, I don't even know why I try, because you know what I mean, right? So then basically this jump here, and then this jump here, and then this jump here, and so on. And then you have a final jump there. They are all jumps that are associated with the jumps relative to the boundary that lives on the plane, right? And so we're trying to plot that, right? That's kind of the idea. Okay, good. And so the way that we plot it is, well, first I show you the domain of the function, and then I plot the function along the boundary. And so that's exactly what I'm doing here. Of course, I stretched it now. And then the kink is B21, which is exactly this point here, right? And so remember that I told you, well, it could happen that near the kink, you might have a little bit of bias. Sometimes it happens, sometimes it doesn't, but that's kind of how you would get it. Okay, excellent. So now let me show you in the last few minutes how we do this. So for that, I also put some code that I hope is going to be shared with you guys, which uses this application. And so now I can show you a little bit of these plots and how things are done in this case. Okay, so let me first remove all this. Okay, and then I'm going to read this data. Okay, it's a little bit large, so we have to be a little bit more careful. And then the first thing I'm going to do is I'm going to create the evaluation points along the boundary. And this is kind of crucial. This is the part that we cannot really work with in the software because, I mean, we don't know what the boundary is. The geometry of the boundary can be whatever. So you have to generate the grids along the boundary depending on the problem that you face. If it is a geographic RD, then you have to use GIS or something else and generate the grids along the geometry of the boundary. In this case, it's actually quite simple because if you remember, it's a Leontief boundary, right? And so I know exactly how to generate grids over that. And so this tiny little piece of code, what it does is effectively generates grids, in this case, 40 grid points, just like in the plot that I show you, so just like here, right? So it's going to generate the coordinates of these 40 points, right? And that's important because once I have those 40 points, now, given that position on space, I can compute the distance from each observation to that, or I can just do the estimation directly on those points. And so first I need to generate those points. And so this is exactly what I'm going to do with this tiny little bit of code. And I'm going to call it in this simple example, X1 and X2. Okay, so pretty straightforward, nothing crazy. So my X1 and X2 literally contain, well, if you normalize, I think we normalize, right? So we put 0, 0 at the kink. So it will be in the X coordinate, it will be 0. And then in the Y coordinate, it will go up to whatever number. And then I go in the other direction. So I keep, well, you know what I mean. Okay, good. Excellent. So that's that. I mean, we can inspect it if you want, but it's pretty obvious, I think. Do I have that somewhere? Here. Let's see. Yeah, exactly here, right? So we do go 0, 40, 38, 36, and then it goes to the kink, which is 0, 0. Yeah, perfect. And then we keep moving in the other direction. So literally we're plotting an L, basically, and those are our tiny little points. Okay, good. Excellent. Now I need to be able to get back to the code. Oh, here, perfect. Excellent. Okay, then we can do the scatter plot. And so for that, I'll just do all the scatter plot at once. It's not super important today, but so you can see a little bit how this looks like. Okay. So it's a lot of data, so it will take a little bit of time, but I want to use it to show you the discreteness in one of the dimensions, right? And so again, if you don't zoom in, then the discreteness is not that bad. But when you zoom in, the discreteness is quite bad. So but the picture looks like this. So here you cannot really see it, but the actual picture that I had was much nicer because you can see actually all the vertical lines running this way, because of course it's 100 points that you can use. But then of course, because of the smoothing on the other direction, then the bivariate vector is continuous in a sense, right? So, and therefore it looks more like a cloud of points. Okay, very good. Not a big deal. You can try later and fix my code. It's online. Okay, good. Okay, so then let me show you what is the most important part. So now here we're gonna grab the data, And now we're gonna estimate this guy. Okay, that's good. So let's do it. Okay. And so this one's gonna take a little bit of time, and this makes sense. Why? Because think about it. We're going over 40 points. So maybe I should walk you a little bit of what we're doing here. So we give the y, and then for each y, we give the position in space, right? So you have the x1, x2, right? Where you are, right? And then you tell me whether you are treated or not. And then you tell me what the boundary geometry is. So this B here will have the coordinates that determine the boundary, right? And so now what the software is gonna do, literally, if you go into under the hood, it's gonna grab each of these points, it's gonna position itself in the position of the boundary that you are, and then it's gonna look at all the data that has around it, and then it's gonna do estimation. So it needs to choose a bandwidth, estimate things, whatever, and then after it's done with that, it's gonna move on to the next point, and it's gonna repeat the process, right? And so that will take 40 times what it would have taken to run one of these guys. Oh, that explains a lot. Okay, good. At least we know now that something was not quite correct. Okay, excellent. And now, is this running?
Oh, yes, sir, thank you. It took a long time to,
It came.
Yeah.
Oh, I told
pretty
you.
large.
Yes. But again, it looks so much better when I had it this morning. It doesn't make me happy that it looks like this. So anyway, but if we zoom in, you will see that there is a bunch of lineup points, right? So the lineup, well, you don't see that, but I see it. So a bunch of lineup points is because of the discreteness that is kind of important in this direction, right? So that's kind of what I wanted to say. Okay, good. That was not very effective pedagogically, but it's okay. Okay, now I wonder why this is not running.
It is running. You see the background. You see the red dot? It means that it's still running.
Which red dot?
The red stop sign.
Oh, the stop sign here.
That means you want to stop and you click it, but it's still actually running in the background.
It's running in the background. Oh, okay. So let's leave it alone then.
Yeah.
Yeah. I don't like to intervene with runs. It's kind of not my thing. Yeah. I don't like it. No. Let's leave it as it is. So do you know how long it's gonna take though?
You might actually wanna delete the figure because it's actually run.
Oh, how do I delete the figure?
Click on the broom. You see the broom?
Yes.
And then it will erase it.
Oh, now we have more problems.
Yeah.
Now we have the clear.
But once you get rid of the figure, you'll have more run. Keep running the.
Okay. This is frustrating in multiple ways because I wanted to show you the stuff.
Bivariate illustrations.
Bivariate. Actually it's representing my point exactly. You know that when you go from one dimension to two, things get much harder. You know, like Should I be worried about this? You know, like if I'm in a plane, I may be in trouble, no? So what should I do? It says like it's a fatal error. I mean, I don't have much options. No, I don't have a choice. Okay, so what happens if I kill everything? Okay, it's a fatal error. Okay, well, I don't want to be fatal, I guess. No, fatal. Okay, good. You know what? I'm gonna do this now because I did this last time. I'm not gonna do the plot, but I'm going to do, I'm gonna do up to here, and then, okay, that seems to have worked.
Yeah.
Okay, good. And now I'm gonna do this. Look, I'm just gonna run the estimates because the estimates is what I wanted to show you. So to run the estimates, I'm gonna skip the plot, which is not that important anyway. Okay, here we go. And so now I'm gonna run up to here. Okay, let's see if we get lucky, guys. I hope we don't have another bomb coming to us. Yeah. Okay, so now I don't have the plot. I have a lot of RAM, hopefully no bombs. This morning it ran much faster, But then again, I was not paying attention because I was in a meeting. Let's see.
If it's a Windows computer, they run much faster plugged in, if it's not plugged in.
Plug into where?
Power.
Oh, yeah, no, it is plugged in. It's
Okay,
plugged in,
that's
it's plugged in. Yeah, but my computer is very old. So this computer is from many, many years ago. I need to change it, but I'm reluctant to change. Okay, this is frustrating in more than one way. I thought it could be that we have many things open or something. I don't know. Yeah. Okay. Okay, that's not very good. Okay, let's give it one more minute and then. So what I wanted to show you was basically the output of this. What it would have is essentially for each boundary point, it will give you exactly the same results that I showed you before, a point estimator, and then a confidence interval construct with linear and quadratic fit, like before, but clearly it's not going to do it for me. Oh, well, any questions in the meantime? Yes.
This is more of a conceptual question, but something I really struggle with going from the single variate case to the bivariate cases. With the single variate case, like I know as I move farther away from the threshold, I know the order is what it is.
Yeah.
But when I'm going from like a bivariate case, now I don't know how to rank these points anymore, which I find very hard to think about.
Yes, and that's exactly the point, right? And so that has both conceptual effects in terms of how you interpret what data you're using for learning and borrowing information at each point, at each cutoff point, but also it has a technical implication because it changes the way that you should select the bandwidth, how you should metrize distance, and many other things. Absolutely. Okay, so it ran, that's very good. So it's all storing here. And then what I'm gonna do is I'm gonna ask a summary that is gonna do something for us. So it's gonna grab the object that it came out. So it contains the estimates along the boundary for each point on the boundary. So we have 40 of those. And then it's gonna do two things at the same time. It's gonna construct uniform confidence bands. So that basically means it's gonna construct the joint inference for the entire 40 points. And then also it's gonna only report for these points that are here. Okay, so that's a subset of the points that we constructed, right? So let's do that. Okay, here we go. Okay, and so now you can see that the output is very, very similar as before. So the number of observations is fairly large. That's why it took a little bit longer. It's 360,000. And then you're still doing mean square error bandwidth. You're still doing kernel triangular. The variance estimation uses something else. It has checked for mass points. Okay, that's important, although again, it has some mass points. And then number of observations are here, right? And now you can see that there is not that many equal values of observations, okay? And then what else? Let me think about that for a second. Okay, and then here is a subset of the results, right? So this is 0, 40. So that number is basically B1, right? So it's 0, 40, right? It's B1, right? And so for B1, it's going to report a point estimate. And the point estimate that it's going to report is exactly this number here, right? So effectively, that's the number that I'm plotting along the thing. And then I move on to 0.032, 0.022, and so on. I'm moving myself down the L-shaped boundary. I hit the kink. And then after I hit the kink, I start moving myself horizontally. And then I have myself all the point estimates that are here, right? And then I have p-values and confidence bands and everything else. For this one ran very fast because by default we have very few simulations. So in practice, you should increase the number of simulations, not just run it by default as it is, okay? But then once you have these, now you can do other stuff. So for example, you could compute the average of these effects, or you can compute the largest of these effects. So you can actually look at what is the average effect, or what is the best treatment along these treatments. And so that you can do as well. So I'm going to show you, right? So you come here, and for example, this one will compute the average, okay? So here we say compute the weighted average, boundary average treatment effects, where the weights in this case are exactly this, okay? And so the weights in this case are just the number of observations that you have. I mean, it's a very simple weighting scheme for simplicity, okay? And so it will look like this. Okay, so now the output has this line here that tells you, okay, this is the average effect along the boundary. So you grab all these effects. Now I show you all 40 of them, right? For a change. So you grab all the 40 effects, compute the weighted average, and then you compute the standard errors and the confidence interval for that. So that is equivalent of the band approach, but the other way around. You first estimate treatment effects individually along the boundary, and then you average them. And then if you care about the largest effect, you can also do that. And now you ask for the largest boundary average treatment effect, right? And the largest boundary treatment effect is now this number here, and these are the confidence intervals for it. This takes some work to get, and this number here will be one of these numbers that is largest, right? And so if you remember the plots kind of showed that we didn't talk about the substance here today, but you can see that there is a little bit of heterogeneity, right? Because when I move myself in this direction, the effect is more or less constant. When I move myself in this direction, the effect decays, right? So the largest value will be somewhere in this region, and it turns out that it is 3361, which happens to be somewhere in that region, right? So 3361, right here, is a 0.11, right? So that 0.11 is where the largest treatment effect happens, right? Which is roughly in the middle of the segment that is vertical which is on the poverty side, right? Well, okay, that's an example, obviously, of how this works. Okay, perfect. And of course, be aware that, well, this you should obviously this confidence interval is for the point-wide hypothesis of this not being equal to 0. The point-wide, the confidence interval for the supremum is different, right? Because you are asking what is the largest value. So it's a different statistic. Is this number, the number is the same, but the statistic is different, and therefore the confidence intervals are different as well. Okay, very good. So it's 3 p.m. So let me just finish off with showing you one more picture. I'm not going to generate now, but this is again, these are the treatment effects. You can put confidence intervals, confidence bands, and then you can even generate heat maps, which I find quite cool, because then you can show large treatment effects, low treatment effects. And again, this is a simple example with an L in a geographic setting or some other interesting setting. You can see interesting patterns of treatment effect heterogeneity. Okay, very good. And with that, these are the numbers I was trying to, instead of showing you slides, just do it for you, but it's a kind of the same idea. You can estimate using the pooling approach, or you can estimate by aggregating after you estimate heterogeneity. So I show you these ones today along the average, right? And that gives you different things for you to play with. And with that, I think we're done. If you're interested, package, which is not super fast, but runs. And well, also, this is like the lower bound, right? Because my computer, but you guys have faster computers, you're younger, so I'm sure it will run faster. And then here's the software if you're interested. Okay, I'm done. Thank you.